In the realm of cosmic research, GN-z11 is considered nothing short of a superstar in astronomy circles. Spotted by the legendary Hubble Space Telescope, this extraordinary object was pegged as the most distant galaxy ever observed, sporting a red shift of Z=11. For those unfamiliar, that's a fancy way of saying we're not just seeing a galaxy far away in space, we're seeing it as it was just 400 million years after the Big Bang itself. Think about that for a moment. The universe was essentially a baby, barely 3% of its current age, still in the earliest stages of forming stars, planets, and the structures we now know. And yet, here's this galaxy, already shining bright, already packed with stars, and perhaps hiding who knows what else inside its compact structure. When the James Webb Space Telescope came online in 2022, bringing with it the most ridiculously powerful infrared eyes humanity has ever aimed at the cosmos, it turned its attention toward GN-z11. What Webb found has astronomers across the globe practically losing their minds. This is no longer just about identifying a distant galaxy. This is about confronting a cosmic mystery so deep that it is forcing us to rethink the very foundations of how the universe works. First, let's slow down and talk about GN-z11 itself. This galaxy is more than just another entry in a deep space catalogue. It's essentially a fossil from the dawn of time, located roughly 13.4 billion light-years away. That means when we look at it, we are literally peering back into a universe that was still figuring itself out, still assembling the first large-scale cosmic structures. Most galaxies from this era, based on our models and previous observations, are small, irregular, scrappy little things, like scattered cosmic debris just beginning to clump together into something recognizable. But GN-z11 is different. It's surprisingly bright, surprisingly compact, and incredibly well-formed for something so ancient. It's almost like walking into a primitive settlement from thousands of years ago and finding a fully furnished modern mansion in the middle of mud huts. Astronomers using Webb's NIR-SPEC instrument locked in GN-z11's redshift with incredible precision, confirming it as one of the earliest galaxies we've ever seen. But the real shocker didn't come from the confirmation. It came when researchers dug deeper into the data. Something monstrous appears to be lurking inside GN-z11, and whatever it is, it's not behaving like anything we've documented before. Here's where things start to get wild. GN-z11 isn't just a galaxy. It's home to a supermassive black hole. And not just any black hole, but one with a mass about 6 million times that of our Sun. That's already huge by any standard, especially for such an early period in cosmic history. But what's even more mind-bending is how fast this black hole is eating the matter around it. Black holes, as you might know, don't emit light on their own. They are invisible, cloaked by their event horizons, those infamous points of no return where even light cannot escape. However, when they feed, they pull in gas and dust that spiral inward, heating up as they fall into a blazing hot region known as an accretion disk. This disk gets so hot it can shine brighter than entire galaxies, and such a system is called an active galactic nucleus, or AGN. The AGN in GN-z11 is screaming with light, and here's the kicker. It's devouring matter at a rate 5 times higher than the Eddington Limit allows. This is where we need to pause and unpack what that means, because the Eddington Limit is one of the key physical constraints we thought we understood about black holes. Named after the astrophysicist Arthur Eddington, this limit is like a cosmic speed limit for how fast a black hole, or a star, can consume material. Here's the basic idea. When a black hole pulls in matter, the process generates intense heat and radiation. That radiation pushes outward against the incoming matter in a kind of cosmic tug-of-war. If the black hole tries to eat too fast, the radiation becomes so intense that it physically pushes the material away, preventing it from falling in. Kind of like trying to pour too much water into a glass, only for it to spill over the edges. The Eddington limit sets the maximum rate at which a black hole can consume matter before this pushback effect kicks in. For a black hole the size of the one in GN-z11, calculations say it should be able to swallow about the mass of our Sun every few decades. But this one? It's gobbling up the equivalent of 5 suns worth of material every single year. That's not just fast. According to our current physics, it's flat out absurd. So how is this even possible? Roberto Maiolino, a well-known astrophysicist from the University of Cambridge, led the team that spotted this anomaly. He called it a game changer. In his own words, it's way too early in the universe to see a black hole this massive and eating this fast. We're talking about a universe less than 1 billion years old here. Conventional wisdom tells us that supermassive black holes require billions of years to grow to these sizes. They typically start small, perhaps a few hundred times the mass of the Sun, and then bulk up slowly over cosmic time by accreting gas or merging with other black holes. But GN-z11's black hole is already a giant, and it shows no sign of slowing down. It's like finding a fully grown T-Rex stomping around in a dinosaur nursery. It simply doesn't fit the timeline. One possible explanation is that the early universe was like an all-you-can-eat buffet for black holes. Right after the Big Bang, space was dense with vast gas clouds. These clouds could collapse under their own gravity to form stars and black holes at a breakneck pace. Maybe some of these black holes got a head start, ballooning into massive objects in just a few 100 million years because the supply of raw material was practically unlimited. Another idea is that these early black holes didn't grow in the slow, steady way we've assumed. Perhaps they went through wild growth spurts, merging with other black holes, swallowing entire star clusters, and doing it all in chaotic cosmic pileups that gave them huge boosts in mass. Whatever the process, it's becoming clear that the early universe may have been a far crazier place than we imagined. But wait, there's an intriguing twist. Some scientists are beginning to wonder if we've been misreading GN-z11 entirely. A team from Oxford took a much closer look at the galaxy's light, paying special attention to the chemical fingerprints embedded in it. When you analyze a galaxy's light, you can determine its composition, elements like nitrogen and oxygen, for instance, which are forged inside stars and scattered into space when those stars explode as supernovae. In GN-z11, the nitrogen-to-oxygen ratio is, well, let's just say it's bonkers. It's 4 times higher than what we see in the universe today. That's not just a statistical oddity, it's a cosmic red flag. This suggests that something other than a ravenous supermassive black hole might be responsible for the strange signals we're picking up. So, what could it be? One possibility is that GN-z11 is undergoing an intense burst of star formation rather than being dominated by black hole activity. Stars form from collapsing gas clouds, and in the early universe, those clouds were almost pure hydrogen and helium. When massive stars die as supernovae, they create heavier elements like nitrogen and oxygen. A sky-high nitrogen ratio could mean GN-z11 is pumping out stars at an insane rate, with supernovae exploding left and right, forging elements in a kind of cosmic industrial frenzy. Another possibility is a tidal disruption event, when an unlucky star ventures too close to a black hole and gets ripped to shreds. This can release a burst of light and energy that might mimic some of the signals we're seeing. There's even a theory involving runaway stellar collisions. Imagine a dense cluster of stars smashing into each other under gravity's relentless pull, creating heavier elements in the chaos. The Oxford team isn't ready to dismiss the black hole idea entirely, but they are urging caution. Let's not jump to conclusions, they say. The data is rich, but it's messy. Interpreting it is like trying to solve a 1,000-piece puzzle when half the pieces are missing. That weirdly high nitrogen ratio could still point toward a black hole, or it could be evidence of something entirely new. Perhaps GN-z11 is a rebel galaxy, rewriting the rules for how galaxies formed in the early universe. Let's zoom out for a moment and talk about why the James Webb Space Telescope is such a big deal in all of this. Launched in December 2021 after years of anticipation and countless engineering challenges, Webb is like the ultimate cosmic detective. Its infrared vision gives it the ability to peer through thick curtains of dust and gas that block visible light, meaning it can see objects and structures Hubble could never hope to reveal. This is crucial when studying the early universe, because so much of the light from those first stars and galaxies has been stretched into the infrared by the expansion of space itself. Webb is specifically designed to look back to what could be called the universe's toddler years, a time when the very first stars and galaxies were forming from raw cosmic ingredients. Every time Webb points at something new, it's like opening a sealed time capsule, revealing a scene frozen billions of years in the past. And among the many extraordinary objects it has targeted, GN-z11 stands out as one of its most compelling finds so far. During an observation program called JADES, short for JWST Advanced Deep Extragalactic Survey, astronomers noticed something unusual. GN-z11 wasn't just another faint smudge like most galaxies from this era. Instead, it was blazing with light and packed with unexpected features. One of the key factors in making these details visible was gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. This is where the light from a distant object gets bent and magnified by the gravitational pull of a massive object lying between us and the target. In this case, a galaxy cluster known as Abell 2744 acted like a colossal natural magnifying glass, amplifying GN-z11's light and letting Webb zoom in to a degree that would otherwise have been impossible. Without this effect, GN-z11 might have remained just another faint dot in the deep field images. But with the lensing boost, astronomers could identify the signs of either a supermassive black hole or some other extraordinary power source driving the galaxy's furious activity. What's got researchers truly buzzing is not only the size of the suspected black hole or its improbable feeding rate, but the fact that such an object exists at all in such a young universe. It's like stumbling across a fully modern skyscraper in the middle of the Stone Age, a structure that shouldn't logically be there according to our models. Consider this: at around 6 million solar masses, the black hole in GN-z11 isn't the largest ever found, but it is much larger than it should